Number 7 says constant velocity to the right and constant velocity up. Okay, well, constant velocity or zero velocity are the same thing, right? Not moving and moving with a constant velocity both tell you what about the net force? Zero. Yeah, and so if you've got, on this object, you've got 10 newtons to the left and 5 newtons to the right, what do you have to add to it?
5 to the right.
5 to the right. And then you also have to add more, right? Because if you actually read the directions, did you read them? It said you have to add at least 2 forces. And we only added 1 so far. So what I did was I was like, well, I'll just make one going up and call it 5, and one going down and call it 5. Right, to make the net force still 0. You could have called this 9 trillion and 9 trillion, or 1 and 1, or whatever, but these two have to be the same. This one's got to be 5, unless you added more stuff. Does everyone see why there's so many right answers? Okay, but this is the basic idea is that the net force acting on this needs to be 0. Okay. Number 8, the answers were, 8A was B, C, D, E, and F. And 8B was A, B, E, F, and G. Does anybody have any questions about that? I'm surprised if you don't.
Good morning, everyone. Please listen to the following announcement concerning our participation in the Great Arizona Shakeout.
The Great
Quick drill. Right now, drop, cover, and hold on. Drop to the floor now. During a large earthquake,
Should I videotape everybody?
strongly and knock you down. Take cover under something sturdy.
I'm feeling pretty safe right now, guys. I know what you guys doing?
You are looking the safest out of all of us.
Pretty good right now.
Alright.
All right, well,
Table could collapse.
I believe that was the end of that.
Wait, it is?
I feel like it's still going.
Okay.
This was gonna tell us that
Earthquake's over, it's safe to come out. 9, F1x equals F2x, F1y is less than F3, F2y is less than F3, and F1y plus F2y is equal to F3. Questions on any of those? Okay. Number 10, 75 newtons was the correct normal force. What are some errors, what are some other, like why would somebody say that it's 100? What is the mistake that that person is making? What do you sometimes assume? Oh, normal force is just equal to
Gravity.
gravity. So the gravitational force is 100 newtons, so a lot of people would just say, oh, it's 100, because that's opposite gravity, right? The point of this problem is to show you that that's not always true. So you sum the forces in the y direction, you set it equal to 0, and you solve for n, and you get 75 newtons. Number 11, the air resistance force is 624. Gravitational force is 784. Questions on that one?
What did you say?
Air resistance is 624.
Okay, thank you.
Can you do that one on the board?
I will, but first tell me, when you did the sum of the forces in the y direction, did you use positive 2 or negative 2 for your acceleration?
Positive 2.
Ooh.
So now I won't, because I know that's what you did wrong. Because it says acceleration is 2 meters per second down.
Okay.
And we decided down is negative because we subtracted gravity, therefore negative acceleration. Number 12, normal force is 700 newtons, and mass is 71.4 kilograms. So far we're good. Applied force, 357.14 newtons. Questions? Really? All right, number 13. All of the answers are 784. Yeah.
Well, I just want to know, does it matter if you do the triangles like on the bottom?
No, it does not. In fact, I did it, for second period, I did the triangles like on the inside of that, and then for fifth period, I did them on the outside. And the reason was, even though the angle is kind of shown right here, right, that gets a little jumbled when you try to put all your triangles kind of smushed next to each other. So what I decided to do for the next class was to make my component vectors on the outside like this. It doesn't matter. You can just as easily go up and over, right? But then you have two that are like next to each other going up. So this just kind of makes things a little bit more spaced out. But then you have to recognize, yeah, and so what are they?
180 minus 120. divided by 2,
which is
which is 30 each.
30. Yeah, these are 30. If you went up and over, then these are 60, right? So this question was actually a little bit weird because they didn't specifically tell you that the tensions were the same, but they are. Okay, anytime you have anything that's like symmetric like this has the same tension. And if you didn't know that from just looking at the question, you do know that the net force in both directions is 0 because the acceleration is 0. So that means that this and this have to be the same. And if they have the same angles and the same x components, then they have to have the same tensions. Okay, so then you can label your component vectors ty, ty, tx, tx. And then when you sum the forces in the y direction, you set it equal to ma, as always, but acceleration is 0. And there's 2 reasons you kind of know this. One, it's something hanging from 2 strings, which is almost always not moving. And also, they tell you, acceleration is 0.0 meters per second per second. Okay, so then you set it equal to 0. Then you do ty plus ty minus mg. Because the 2 ty's are the same, 0 equals 2 ty minus mg. So ty is mg over 2, which is 784 over 2. Okay. Then, that's not the answer, right? The answer is what is the tension. So if I have the y component and I have the angle, I can figure out what the tension is, right? So using which trig function? Sine. Hopefully all this trig stuff is becoming sort of second nature to you. You see that it's the opposite of the angle and you say sine. Okay, if you see it's adjacent, you say cosine. So if I use sine of 30 equals ty over t, sine of 30, some of you should know off the top of your head.
Round 3 over 2.
1/2.
That's cosine of 30, 1/2, yeah, 1/2 is 784 over 2 over t. The reason I left it as 784 over 2 is because eventually you're going to multiply by 2, so then you get tension is 784. And that's the same for both. So 784, 784, 784. It just so happens to be. Questions about number 13? Okay. The last 2. I'm going to assume you want me to do these problems. Am I wrong?
No.
Okay, so number 14, the answer is 16 kilograms. It's a really heavy book. It's like your whole backpack, maybe. Okay, so it says a book is pushed against the wall with a force of 300 newtons as shown. Now, this is one of those problems that I wrote, and so isn't perfect. It's not a perfect question. I know it's really surprising to you, but sometimes I mess up everything all the time. So if you're pushing upward a little bit against the book, so it sort of makes you feel like without that upward force, it would without friction going down, it would slide up the wall, right? But that upward force, it turns out, is so small because the angle is only 15 degrees that really it's like helping friction to keep the book from sliding down the wall. Okay, so the intention of the problem was that, so if I push straight on a book like this, then the friction force up is what keeps it from sliding down the wall. So I just wanted to add a little bit of difficulty by making an angle, right? So I pushed up a little bit to help friction. So the free body diagram should have the applied force up and to the right, but friction should go with it up the wall. So if you didn't do that, that's kind of my fault, and I apologize, but just know that this was the intention of the problem. And then mg goes down, gravity. And then what's the other force that I need here?
Normal.
Normality? Is that what you said?
The normal force.
Yeah, the normal force. And which way does the normal force go?
To the left. To the left.
To the left. Which is weird. Have you ever seen a normal force go to the left before? No. But it doesn't matter, because if you follow the rules of what the normal force is, right, and you remember the word normal means perpendicular, then it's the surface pushing out Okay, so if you think about this, think about it in the context of the picture, right? The wall is here, and I'm pushing this way, and the wall is pushing back this way. Okay, so then they give you all these numbers, but you want to sketch in the components of your applied force. And this is 15 degrees, this is FA in the X direction, and this is FA in the Y. And then it says something very important. It says it does not move. So, what does that tell you? What information?
Zero.
Yeah, net force equals MA, but that equals 0 in both the X and the Y direction. Okay? And then you follow the directions. It says sum the forces. Sum the forces, set it equal to 0 in this case. So in the X direction, I have all of the right forces minus all of the left forces. So FAX minus N. Unfortunately, this doesn't help us at all. But it's a good habit to get into to just do it anyway. Okay? And then in the Y direction, you take all of your up forces. Luckily, I put arrows on my component vectors. Up, up, down. So I do plus FF plus FAY minus mg. And that's where the magic happens, because you're looking for the mass of the book. So I have that the applied force is 300 newtons. So I can find FAY, 300 sine 15, which somebody told me was 77.6 newtons. Okay? And then this was 80 times 9.8. Oh, no, whoops. It was just 80. This was 80. Sorry. The frictional force was 80. I should just read the question. It's right on the paper. But anyway, so we plug in our numbers. 0 equals 80 plus 77.6 minus mg. Add mg to the other side. 157.6 divided by g. And you get 60. Oh, sorry. 16 kilograms. 16 kilograms. Does anybody have any questions about the process that I followed to do this? The process is the same, right? 1-2 punch, free body diagram, Newton's second law, in the X and the Y direction. And it turns out in this case, you know, if this were a test and you had answered the test question and never written down the X direction at all, that's fine. Okay, but I did it just to kind of to follow through with the entire process. Okay. I like this question because it makes you rethink how you draw free body diagrams. If you just automatically start like normal force goes up, then you get messed up. But if you think through the problem each time and you really think about what's happening, then the normal force going to the left isn't like something crazy. It's just so happens to be for this problem that the normal force goes to the left. All right, number 15. The answer. Normal force is 2,908, and frictional force is 35.2. So, let's do that one. It all comes down to drawing the free body diagram properly, because when you're summing the forces, you're referencing that free body diagram again and again and again and again and again. So, let's start with the easy stuff. You got some sort of box or crate or something. There it is. And then, what are the forces? Gravity and normal force. Normal force goes straight up because it's along a horizontal surface. What else do we have?
Frictional force.
Friction, and that's going to go which way?
To the left.
Straight to the left. 2 applied forces. Okay, it's weird because in the picture, one looks like it's acting on the left side and one looks like it's acting on the right side. There are no sides to this. This is a point mass, we call it. It doesn't have any extended shape to it. So all of the forces are acting on it here. Okay, so all of your force vectors for a free body diagram should originate here, which means that you're going to have one that goes up and to the right, call it FA1, and you're going to have one that goes down and to the right, FA2. It looks kind of funny, but that is the circumstance. Okay, now we have 2 forces that are at angles. So what do? What's the next part of drawing this free body diagram? Yeah, drawing the components, and they're gonna be sort of like overlapping each other, which I know is kind of weird, but I just put them next to each other like that. Just to remind myself that there are two of them here. So when I go back later to look, I don't just see one arrow. And then this is 20 degrees, and this is 30 degrees, and this is FA1X and FA1Y. FA2X and FA2Y. So many subscripts. Okay, so then all the hard part is done, right? So then it says, same thing as always, what is the normal force and the frictional force? You've got some sort of acceleration. So Newton's second law in the x direction and in the y direction. So then you ask yourself the question, is it accelerating in the x direction?
Yes.
And how do you know that it's accelerating?
Because it tells you that it accelerates at a rate of 0.8 meters per second squared.
Yeah, it says here's the acceleration of it, right? So it couldn't be any clearer about whether it's accelerating. But then you ask yourself the same question in the y direction, what is the answer? Is it accelerating in the y? Why?
Because there's no vertical motion.
Yeah, there's no vertical motion. It's being pushed along some sort of horizontal surface. It's not flying away. It's not burrowing into the ground. It's just not moving this way at all. So in the x direction, we leave it as ma, but in the y direction, we set it equal to 0. But then from there, when you actually sum the forces, you just take all the right forces minus all the left forces. So we have right, right, left. Okay, so it's going to be FA1x plus FA2x minus FF. Notice I know which direction those forces are pointing because I put arrows on my component vectors. Right, right, left. In the y direction, I do all the up forces minus all the down forces. Up, up, down, down. There are 4. It doesn't make the process any different. It just adds something to it. So now we have n plus FA1y minus FA2y minus mg. And I think you guys can do the rest of this, right? You know how to find the components, you know how to find the sides of the triangle, and you know how to plug numbers into an equation.